Today we're going to talk about the definite integral, section 5.2, and this has to do with Riemann sums. So here we have a figure of rectangles extended from the x-axis to intersect the graph of y equals f of x at points c of k and f of c of k. Approximate the region between the x-axis and the graph. So these rectangles are approximated in the region between this x-axis and this graph. In our next definition, when we talk about it, we're talking about this picture here. So the definite integral as a limit of Riemann sums. So let f be a function defined on a closed interval ab. For any partition P of ab, let numbers c of k be chosen arbitrarily in the subinterval xk minus 1 to xk if there exists a number I such that the limit of our partitions approaches 0 of the sum from k equals 1 to n of f of ck times delta xk equals I. No matter how p and the ck's are chosen, then f is integratable on ab, and I is the integral of f over ab. The existence of definite integrals. All continuous functions are integratable. That is, if a function f is continuous on an open interval ab, then its definite integral over ab exists. The definite integral of a continuous function on AB. Let f be continuous on AB, and let AB be partitioned into n subintervals of equal length. The change in x equals b minus a over n. And then the definite integral of f over ab is given by the limit as n approaches infinity of the sum from k equals 1 to n of f of ck delta x, where ck is chosen arbitrarily in the kth subinterval. So the definite integral. This is what a definite integral looks like. That long S is the integral. B is my upper bound. A is my lower bound. F of x is my integrand. And dx is my variable of integration. Let's look at our first quick quiz from section 5.2. The expression 1 over 20 times the square root of 1 over 20 plus the square root of 2 over 20 plus the square root of 3 over 20 all the way to the square root of 20 over 20 is a Riemann sum approximation for which of the following? So take a minute, pause the video, and try to answer this question. Hopefully you chose B. So here, this is the interval width with a right rectangular approximation method. So there's 20 subintervals, and the subinterval has width 1 over 20. So that means my integral will go from 0 to 1. Since there's 20 subintervals of 1 over 20, it starts at 0 and goes to 1 of the square root of x. Let's look at example 1. In this one, you're going to use your calculator for. So I want to find the definite integral from 0 to 3 of x squared times sine x dx. So in your calculator, you will go ahead and choose math and then the number 9. And the number 9 is the finite integral. In that, it will either have, this will pop up where you can plug everything in, or you would just first plug in x squared sine x, then your variable of integration, then your lower bound and your upper bound. Otherwise, and you press n equals and you'll get 5.776. Otherwise, in your calculator, this will show up. A box will be here. You put the 0 here, the 3 here, then inside you put x squared sine x. There'd be a d here, and you just have to put in the variable of integration x, and round into 3 decimal places, you get 5.766. So I have a question for you. Is the area between a curve y equals f of x and the x-axis on the interval ab the same as the definite integral of f of x from a to b dx? So the answer is sometimes. And you'll see that in the next examples. So area is different than actually evaluating the integral. So area under a curve as a definite integral. If y equals f of x is non-negative, so the key word here is non-negative. So that key word of non-negative and integratable over a closed interval AB, then the area under the curve from f of x from a to b is the integral of f from a to b. However, area of an integral when f of x is less than or equal to 0 is the area above the x-axis minus the area below the x-axis. Because the area below the x-axis, since it's below the x-axis, its value will be negative. So if you are asked to find the area of a curve, you need to take the area above the x-axis minus the area below the x-axis. So let's look at example 2, find an area using geometry. Evaluate the integral from negative 2 to 2 of the square root of 4 minus x squared dx. So you should know what this looks like. So if I were to graph this, it is a semicircle from negative 2 to 2. And it would look like this. So if I wanted to find it would just be the area of the semicircle. And the area would be pi r squared divided by 2. So this would be pi, my radius, if this is my center, goes out to 2. 2 squared all over 2, which would equal just 2 pi. Example 3. Integrals of discontinuous functions. Evaluate the integral. So this we're just going to evaluate the integral. It doesn't say find the area of the square root of x over x dx from negative 2 to 2. So let's go ahead and draw this. You should know what this looks like. So this would look like this. And if I look at this, the area here is 2, and the area here is also 2. However, it says just to evaluate the integral. If I were to evaluate this, this would equal 0. Because this value here is negative 2. This value here is positive 2, so it would be 0. But the area is equal to 4. However, they just wanted you to evaluate the integral, so it would be 0. Let's look at the last quick quiz. Question. Evaluate from negative 4 to 4 of 4 minus the absolute value of x. So take a minute, pause the video, and try to figure this one out on your own. So hopefully those of you who tried it on your own got 16. If you were to graph this, it would look something like this. And that is a square, 4 by 4 squared. So 4 times 4 is 16. So our integral would be 16. And notice both of these are positive. So that's why it's 16. And you don't have to subtract the negative to get it.